Assalamualaikum everyone. In this episode, we'll bring back an excerpt of a past upload on hydrostatics, focusing on buoyant force or upthrust and gauge pressure. So join me, stick around, watch and learn. The question is, a cubical block of wood 10.0 centimeters on a side floats at the interface between oil and water with its lower surface 1.50 centimeters below the interface. The density of the oil is 790 kg per meter cube. Question letter A. What is the gauge pressure at the upper face of the block? Question letter B. What is the gauge pressure at the lower face of the block? And question letter C. What are the mass and density of the block? As shown in the figure, we have a cubical block of wood 10.0 centimeters on a site. The block floats at the interface between oil and water. We're given the density of oil, 790 kg per meter cube. Also, the lower surface of the block is 1.50 meters below the oil-water interface, denoted here by small letter h. All right. So this depth of the water from the interface to the lower face of the block is given as 1.50 centimeters. Here are the target variables in this problem. We have letter A, the gauge pressure at the upper face of the block. We also have the gauge pressure at the lower face of the block. All right. So the gauge pressure at the upper face is denoted by P sub G1. All right. Meaning the gauge pressure at the upper face, which we label as 1, while the gauge pressure at the lower face of the block is labeled as P sub G2. All right. And the third target variable is the mass of the block as well as its density. To calculate for the gauge pressure at the upper face of the block, we just use the formula P sub G1, all right, equal to the density of oil times the depth h prime and acceleration due to gravity, where the depth h prime is in fact equal to the depth h. which is given in the problem to be equal to 1.50 centimeters. Likewise, to calculate for the gauge pressure at the lower face of the block, all right, we use this formula, P sub G2 equal to the pressure associated to the entire depth of oil equal to 10.0 centimeters or 0.100 meters, all right, plus the gauge pressure of water at a depth h. All right. So as emphasized in the drawing, we use this colored portion of the liquid oil. All right. The total depth. All right. The total depth of oil is actually given in the drawing, which is 10.0 centimeters. All right. And that of water is colored blue. All right. So this colored portion of the volume of water has a corresponding depth, all right, already defined earlier as h. So the portions of oil and water that are colored yellow and blue respectively corresponds, all right, or has a corresponding pressure labeled here as P sub G2. This is the combined pressure that the two liquids exert on the lower face of the block of wood. For question letter C, where we are looking for the mass of the block as well as its density, right? So we just apply the definition of upthrust or buoyant force, right? Which is equal to density of the liquid multiplied by the volume of the liquid displaced and acceleration due to gravity, all right? So in the case of oil, the upthrust exerted by oil, we label that here as F sub B oil. That's equal to the density of oil multiplied by the volume of oil that is displaced by the block of wood and multiplied by acceleration due to gravity. All right. Now for water, the buoyant force or upthrust exerted by water on the block of wood is just equal to the density of water multiplied by the volume of water displaced by the block of wood and of course times acceleration due to gravity. Then the combined upthrust or buoyant forces exerted by oil and water, all right, is just actually equal to the weight of the block of wood because the block of wood is said to be floating in the oil-water interface, meaning the block of wood is in static equilibrium. So, the net force on the block of wood, we say, is equal to 0. And after getting the mass, based on this definition of the total buoyant force being equal to mg, all right, after getting the mass, we can proceed in calculating for the density of the block of wood simply by dividing its mass by its volume. Moving on now to our computations, starting with the gauge pressure at the upper face of the block. All right, our formula is P sub G1 equals density of oil multiplied by the depth h prime and acceleration due to gravity. So substituting, all right, we have gauge pressure P sub G1 equals 790 kilogram per meter cube. Okay, that's the density of oil multiplied by 0.0150 meters. That's the value of h prime, and 9.80 meters per second squared. Of course, that's the value of g. So doing our math, we get this gauge pressure number 1 equal to 116 Pascal or Newton per meter squared. All right, notice that we obeyed the rule of significant figures. So our answer has 3 significant figures. Now, for the gauge pressure P sub G2, meaning the gauge pressure exerted on the lower face of the block, all right, which we said the formula is just multiplying the value of acceleration due to gravity, okay, by the quantity inside the bracket, okay, where we have the density of oil multiplied by 0.100 meter plus the product of the density of water and the value of H, all right, and substituting, we get 9.80 meters per second squared multiplied by the quantities inside the bracket, such as 790 kilogram per meter cube, which is multiplied to 0.100 meter, all right. Their product will be added to 1.00 times 10 to the third kilogram per meter cube. That's the density of water to be multiplied by 0.0150 meters. All right. So again, simplifying or doing our math, we will get the value for the gauge pressure P sub G2 exerted at the lower face of the block, and that is 921 Newton per meter squared or 921 Pascal. Again, it's also expressed in 3 significant figures. For question letter C, where we're going to find the mass of the block and its density, all right, we will again base it on the formula for buoyant force, which in the case of oil, the buoyant force exerted by oil is just the product of its density, all right, and the volume of the oil that is displaced, and of course, acceleration due to gravity. But before we can calculate for this buoyant force or upthrust exerted by oil, we first have to calculate for the volume of oil that is displaced by the block, which is simply equal to the volume of the block that is immersed in oil. All right? And this is determined by just multiplying one side of the block 0.100 meters by another side 0.100 meters and 0.0850 meters, or the volume of the oil that is displaced will be 8.50 times 10 to the negative 4 meter cube. How did we get 0.0850 meters? Well, that is just actually the difference between one side of the cubical block, all right, 0.100 meters and 0.0150 meters. Okay, 0.0150 meters is actually the depth h or h prime. All right. Take note that the block displaces a volume of oil less than the volume of the whole cubical block, and that volume of oil that is not displaced by the block has a corresponding depth equal to 0.0150 meters. That's why it was deducted, all right, from 0.100 meters, and the difference is 0.0850 meters. All right, so now we have the computation for the buoyant force exerted by oil, okay, just equal to the density of oil, 790 kilogram per meter cube, times uh, the volume of oil that is displaced, 8.50 times 10 to the negative 4 meter cube, and acceleration due to gravity, 9.80 meter per second squared. All right, doing our math, we get the buoyant force exerted by oil on the block equal to 658 newtons. Similarly, we use the formula of buoyant force for water. All right, but we first find the volume of the water that is displaced. So this is equal to 0.100 meters times 0.100 meters, and all right, the depth h corresponding to 0.015 meters. Okay, the result of which is equal to 100 or 1.50 times 10 to the negative 4 meter cube. All right, so with that volume of water displaced, we can proceed now in computing for the buoyant force exerted by water. So that's just equal to the product of the density of water, 1.00 times 10 to the third kilogram per meter cube, multiplied by this amount of the volume of water displaced, 1.50 times 10 to the negative 4 meter cube, and acceleration due to gravity, 9.80 meters per second squared. So doing our math, we will get the value of the buoyant force exerted by water equal to 1.47 Newton. So adding the two buoyant forces, all right, uh, the buoyant force exerted by oil, 6.58 newtons, plus the buoyant force exerted by water, 1.47 newtons, we get the combined upthrust or buoyant force exerted by the two liquids equal to 8.05 newtons. And this combined upthrust is just equal to the weight of the block mg, right? So we can isolate the mass m, all right, and calculate for it by just simply dividing the total buoyant force, 8.05 newtons, divided by acceleration due to gravity, 9.80 meters per second squared, and we get 0.821 kilograms as the mass of the block of wood, all right? So just like the other computed values, this one also has three significant figures. And finally, we can now calculate for the density of the block of wood, simply dividing the mass that we calculated here, all right, by its volume. That is 0.821 kilogram divided by 1.00 times 10 to the negative 3 meter cube for a density equal to 821 kilogram per meter cube. So that's all for now. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.